April, can you join the Zoom session and share your screen and show everybody where that student software? April's going to show you guys a really important link for you. It's a little different on the staff account, so. This first one that she's clicking on is the Microsoft Azure for Learning free software site. And if we click on this link here, the Azure for Learning website, you can watch the video at home, but we should be able to go to this site here. You just click sign in, and you're going to try your OTC account. This Azure for Learning site is just for CIS students. So Dr. Ford has to set up your account. So there's a chance we might not all be set up yet. Or it might not load at all, huh? So it has a link to OTC to show you that sign in. Press refresh. Let's see if it does anything. The other thing we could try out of desperation is using Internet Explorer. Weird thing. So this is a Microsoft website. Sometimes you have to use Internet Explorer for things to work right. Sometimes it just doesn't work. So we will revisit that one later. Let's go back. Microsoft has just been changing it a lot. But on that site, you'll be able to get software like full copies of Visual Studio and Windows 10, different things like that. Now, the Office availability link really is just taking you to office.com, and you have to click Get Started. Or actually, she sees what to do. Enter your school email address. And you want to do this at home. And when you do, it should take you to the login screen. And if you could just go straight to office.com, let's just do that and log in. Because I don't know what this site is going to take you to. But you're going to log in using your OTC email. And then you're just going to sign in with your regular OTC password. If you're at home, it's going to prompt you for your password. Where here, since you're already logged on, it doesn't. Now, you can go through the setup stuff. You don't have to do that for us. But when you get logged on office.com, you'll see a button to install Office. And you want to use that, and you can get the free copy of Office installed. Just let me know if you run into any trouble, because Microsoft has things so customized and our different computers are so customized. Usually it goes pretty smoothly, but you can run into trouble. The last thing here is Raptor. And Raptor is the flowcharting software that we'll be using in our class. And we'll just be using it through chapter 3 and maybe a little bit in chapter 4. So most of the assignments that we have that use Raptor, you can do in class. But some people like to go ahead and download it at home to practice with it and to work with it a little bit more. It's very, very basic. And so it's very straightforward, and it helps people understand how logic works, like looping and decision making. So some people really like to use it. Now, the link here is going to take you to the Raptor website, and this is just a software developer that developed this tool to help students that are learning to program. So it's not any sort of fancy, software that's sold somewhere or anything like that. It's just used in a few online or intro textbooks. But if you want to install it at home, you're just going to download the latest version. Now, because it's not fancy software, you might get a Windows warning, that this software isn't, hasn't been tested by Microsoft, and that's okay because that's what the software is. It's just a small package. The IT department has tested it and made sure that it was valid as a download for you so that you can go ahead and click to allow or accept or whatever it is that Windows is asking you. Thank you, Randy. Give April a hand. Yay! She's been driving around showing us all these things. Yay! Okay, I'm going to take up. She's got it. So just explore. And I'll get back with you on that Azure for Learning. I'll make sure that your accounts have been created and we've got all of that not up in the air for you. For this week, it looks like there's a lot. These two labs are things that we'll work together on in class, on our lab today and in our lab on Thursday. The other thing that is still outstanding is your Scratch game, and that's due Thursday. Don't forget, we'll take a look at those on Thursday. So we have a few things to do. For homework, the Chapter 3 review questions are out there. It's the same type deal as the Chapter 1. When you click submit, it'll disappear. Canvas will be left hanging, wondering if you've submitted it or not. And I'll be able to see it. You should get an email that tells you it's been submitted. If you want to write those answers down on a separate piece of paper or record them in a separate file and then type them in on that form, that's probably understandable since it kind of disappears that way. All right. Any questions about all of that great stuff? Let's talk about Chapter 3. I've got this PowerPoint, and I have this pseudocode that I'm going to send you. So right now, I'm just looking at it in Notepad. I'm going to drop this file on our Discord channel. So this is going to be a good time for us to help our neighbor and make sure everybody's set up on our Discord channel. And I think most everybody is. I can tell from the swirling squares here that I've gotten disconnected from Discord. If that happens to you, go down to Task Manager and quit Discord and then start it up again. It seems like the firewall sometimes sort of gets upset with it. Let's go find my file again. And you should be able to see that text file on Discord. In this chapter in our textbook, they talk about this sale price program a lot and this pseudocode a lot. And instead of us retyping it, I thought we could just share this file. Now, I have mine open in Notepad, but that's not where I want it. So I'm going to right-click on this file and choose Edit with Notepad++. Or I could open Notepad++ and do File Open and go open this file. So whichever way.
Discord to start working it?
Do I?
How did you say you got Discord to start working it?
You see it? It's like a little white, top half of a face white, sort of puffy cloud looking thing. Did you get it? Thanks. Everybody else okay with Discord? It's not hanging on you? Now I've got our pseudocode open in Notepad++, and we'll look at it as we go through the presentation. I want to delete my date and name here out of it so that everybody's is the same. So we're still talking about developing a program. That's our purpose in life. So we saw in chapter 1 that we're really concerned about the program development cycle. We are trying to solve problems here. We know that we have to understand a problem before we can solve it. And then we have to come up with a plan, carry out our plan, and review the results. One problem, if you're a driver in Springfield, you know sometimes there can be a lot of traffic problems. Well, things are a lot better than they used to be. For a long time, the left turn lanes would get so backed up onto the major roads in Springfield that traffic couldn't pass through intersections, and we would be stuck for a very, very long time. And so there were a lot of people that were really upset about it. They talked about how we needed more lanes, we needed bigger roads, we needed different things, more street lights, all sorts of things. And then finally, somebody really looked at the problem and said, you know, the problem is just all these people trying to turn left. Maybe if we had 2 lanes turning left on some of these major thoroughfares instead of just one, some of this traffic wouldn't get so backed up. So that was their plan to solve it. They carried out the plan, but then they had to go back and look and review the results, right? Make sure that it really helped. And in Springfield, it really did help, right? But there could be another city where that really doesn't have any impact. You know, maybe there's just too much traffic. Of course, we all know our, what's that diverging diamond thing that they invented in Missouri, you know, and they're so proud of, and they should be, because that was a lot of analysis. What in the world is causing all these traffic backups? Same thing when we're programming. We've got to look at this problem and really try to understand it before we can solve it. So we need to make sure that we're understanding the problem from the user's point of view, not just from our, how can I use a really cool solution to solve this problem? Because sometimes we like really cool bells and whistles. So when we're writing a program, we're going to do a lot of the same thing. We're going to analyze that problem, sometimes to death, so we know exactly what the situation is. We're going to design a solution, code our solution as a program, and then test it. And when we're testing, we're going to review and make sure that it's doing what it's supposed to. We aren't just saying, oh yeah, it ran. So we're making sure that it did what it was supposed to do. So we have to know what it was supposed to do. We have to know what our desired results are. What is our output? That's going to be our guiding factor. Are we being able to produce the desired output? Before we can get to that output, that end result, we need to know what kind of input do we need to get started. Here's a cute example. This is always a good one. Someone tells you that they want you to write a program that generates 6 random numbers to be a lottery ticket. And they've used a lottery ticket for some specific reasons here. So we're like, okay, I can generate some random numbers. How about these numbers? Are those okay as a valid lottery ticket? If not, if number 7 was a winning, that would be great. Usually, if we're doing like, I don't know, one of those ones where you random pick numbers, all of our numbers are different. So that one probably wouldn't work. So that's a rule, a design rule, part of our problem analysis for us to find out. We want each of these numbers to be different. We don't want to reuse a number. What about this list of numbers? -3, 0, 8, 9. Do those look okay as a lottery ticket? Be pretty hard to guess if we were going up to numbers as high as 689. Plus we have duplicates again. We probably don't want to include negative numbers or 0. So now we have a whole nother rule. We want a list of 6 numbers that are greater than 0, but less than some certain limit, right? And non-zero. So we're making more and more rules. What about these numbers? 47.98765. That's a pretty specific number. So we'd never be able to get that. So now we've added another rule. They have to be whole numbers, right? Not decimal numbers. So all of these rules have to do with our problem, right? They're like, what are our valid values for these different numbers? So we have to know all those things before we could start writing a program, or we're not going to be creating a program that does what it needs to do. So in the end, we might have something like 6 different positive integers within the range of 1 to 40. That's a pretty specific statement of our numbers. So then we can design the program. We're going to use a lot of different charts and diagrams and pseudocode to design the program. Pseudocode really comes into play most for people that are trying to figure out how to solve a problem. And usually it's used like on spur of the moment type things, like if you've ever heard stories about people designing some great invention on a napkin or something like that. That's kind of how pseudocode is. You wake up at 2 in the morning and you're like, oh, I know how to solve this problem. You can scratch something down really fast in pseudocode. So pseudocode might be something that's official that we share with others, or it might not. But usually our charts and diagrams and things that we create, we're going to share with other people on our project team. We're going to identify those algorithms that we need, our step-by-step instructions that we have. And our algorithms need to be really, really well-defined and well-ordered, and they have to produce some sort of result. And they must get done in a certain amount of time. So they can't just go on into infinity. We want them to produce some results. Solve the problem. So then we're going to take all of these beautiful charts and diagrams and pseudocode and everything that all this design team has created, and we're going to convert that into program code. These might be completely different people. It might not be the people that were involved in the design team. That's why all these documents are very important. We like the idea of thinking, oh, I'm going to go out and write the next greatest app that's going to make me a fortune. And sometimes that happens where that one person or one team does all that problem solving and design and coding and testing and everything. But in a lot of situations, we have different groups that are responsible for these different steps. So our charts and models and diagrams are really important. Could be other people that are looking at them. Now, as we code, we're going to add comments to our code. That'll be our internal documentation, right? We've been doing that already with our pseudocode. When was it written? What's its purpose? All of those kinds of things. And then as we write our program code, we're going to be using a specific syntax of the programming language that we're using, following its coding rules. So some programming languages are going to allow us to do things that other programming languages aren't. So what is syntax? You've probably heard that term before. It's the rules for the language. I like this little statement that they have. They say, the correct syntax for telling your friend where you put a cheese sandwich is, I have put it on the table. That's what we would say. Incorrect use of our English syntax would be to say, I have it on the table put. So all the right words are there, but to us, they're not in the right order. So since it's not proper syntax, the sentence, it may not be gibberish, but it's not as understandable as it should be. But they do mention translated word for word. That second sentence is in the right order for German. So if we were speaking German, that would be the order that we'd have. And we know that when we're speaking with people, we have to use the same kind of syntax. And we see it a lot with electronic communication, right? That's what everybody complains about, that you can't use all uppercase. You know, that kind of syntax in electronic communication. So it's yelling or whatever, if we're texting people. So we have to use the right rules. And then finally, we're going to test. When we're testing, we're going to be asking questions. And sometimes as an instructor, when I ask people questions like this, they might be put off. They might be offended. They might think that a teacher is attacking them, and you shouldn't think that. Not at all. Because it's important for your instructor, your boss, your coworkers to be able to ask you questions like that. Why did you decide to do it that way? Did you interpret that data correctly? Does that program do what it's supposed to? These are important questions. They're not in any way offensive. They're just trying to figure things out. When somebody has a problem, you might ask them, did you use the correct formula? Could we step through it and see if there's a problem with it? So when we want to step through something, we call that desk checking. I want to sit down and I'm going to look at the code and decide if everything looks right. When we're coding, our software that we're using is going to alert us to errors in syntax. So we'll know to correct those. But if we have a problem with our logic, we're not doing something right, the algorithm is off, or we're not interpreting the algorithm correctly, we won't be told about that. We'll have to be doing investigation and analyzing our output to make sure we find those kind of problems. In order to do that, we want to test our program with as many test data sets as possible. And I've asked before if anybody's been a beta tester for games or anything like that, those things are done in order to get as many tests as possible run on a new application. Finally, we're done. We're ready to ship this thing out. We want to do a little bit more documentation, our final steps. We want to do an outline of the program so that it's obvious to others what tasks and subtasks have to be accomplished, what things are dependent upon each other. We want to figure out how we're going to carry out all these tasks as we're developing. And then when we're done, we want to create a user's guide, maybe some help files. We might have to train employees to provide phone or customer support. Maybe even duplicate flash drives or something like that that we're sending out to a bunch of our sites, or advertise the program to attract buyers. A lot of people here at OTC, especially this semester, it seems like, are working for Jack Henry, and I might have mentioned them before. They create banking software, and their headquarters are in Monette, about 30 miles from Springfield, but they have that great big building on 65 in Battlefield, if you've ever noticed that big giant brick building that goes on forever and ever. Well, they're hiring a lot of OTC CIS students, which is really exciting, and they're hiring them after they've had their 120 class and their intro to web dev class to do customer support. So they're bringing them in to do tech support on the phone. So this is a really important step in the career, because what they're telling these people is, come in, do tech support for us now, get to know our systems, so that by the time you graduate from OTC, you'll be ready to take a job in software development and move on in. So it's working out really well. And I was really surprised, because I think there was like 5 people in one of my C#1 classes that are all working over there doing that. So that's a really great thing. I think Jack Henry is seeing the value of the training that you guys are getting, and they're trying to pull people in before they get jobs someplace else. So tech support is a really, really good way to go, especially in school, because you're on the phone. Usually if you're on the phone When nobody's calling, you can do homework and things like that. So it works out really well. Okay, so I hope you have figured this out for me going on and on and on forever about this program development cycle, that this is a cyclic process. Cyclical. I'm making it cyclic like I'm sick, but it's cyclical. It keeps going on and on. It's a never-ending cycle. Whenever we put a system into production or sell it, immediately we start finding problems. So we start working on the next release and pulling together all of our new design ideas that we need to implement, encoding those, and then doing more testing. So that's good for us. Bless you. So we get to do it forever. So here's our sale price program example. That is the pseudocode that we grabbed from Discord. So let's look at this first, and then we'll look at the pseudocode that we have. What our problem is here is we are working for a local department store, and they want to develop a program that takes a product's original price and a percent that it's on sale for, that it's discounted, and it'll calculate the sale price and sales tax. So we want to be able to hold some data that we get from our user. So we need variables to hold the name of that item that we're working with, the original sale price of that item, the tax amount that we calculate, and the total price. So I guess total price would be the sale price plus tax. So we'll see, we might need some additional variables as we go. And there they are. They see that we need to keep track of a couple more things: our original price and the discount rate. Those are things that we're going to prompt the user for. These other variables will be calculating. No, it's a little mixed up. The item name will be prompting the user for. And then we're going to need one more variable to do our calculations called amount saved. And here's the formulas for us. So that's like our algorithms right there. Is how we do those calculations. So we were getting this information and we're like, I don't know. I see some stuff here, but I think I want to clarify this in my head a little bit. Well, I can use an IPO chart. This is an input processing or output chart. We'll take a look at it. It's really simple, but it really helps us kind of to clarify where things are and what we need. So for this application, where we're going to calculate a sale price, we're going to need these three things as input: the name of the item, the original price of the item, and the percent that it's on sale for. Here in the middle in our processing, we have all those calculations that they supplied for us. And then over here, in this area, we have our output. So our output is going to be our total price. Here's that variable being calculated. And our item name, which we said was the input. Our tax, and here's that variable being calculated. And our sale price is being calculated. So I'm going to back up. If I look at this, it gives me a lot of information, a lot of good stuff. It tells me what's going on. But if I look at this, I can see exactly what's going on, right? I can tell where all of my output fields are coming from, how they're calculated, and what I'm having as input. So this IPO chart is a really nice way to organize everything so that we can see it kind of all on one page and know exactly what we have going on in this program. Any questions about it? Seems pretty straightforward. Word is not really helpful in doing these. I'll try. Now, as I develop my programs, I'm going to be thinking about the different functions that this program has to fulfill. What does it need to do? What is its major tasks? Each of those tasks then, I could think of is a separate part of my program, a separate module, right? And that's important because I could have Joanne code one module, I can have Bill code another module, and I can have Jose code another, and then I can put all of these modules together for my testing, and I can separate my work. It's really important, right? Because nowhere in any job field do we have one person that does the whole thing. If you're a carpenter, you don't go in from the beginning and build the foundation, put up the walls, put up the roof, do the wiring, do the plumbing. We have many, many different types of contractors that do those different jobs. Same with software development. We can't just have one master developer that goes in and creates our entire application, our entire system. We need input from several different people if we ever want to get this job done, right? Otherwise, we'll never be done. So I want to separate each program task into a separate program module. Now, these tasks I can think of then as sub-modules or sub-programs. Bless you. And when we split stuff up like that, that's called modular programming. Way back in the beginning days of programming, they just wrote top-down code. Do this, do this, do this. And there was just like one master programmer that wrote this whole application, and nobody else could ever figure out what it did. So as time went on, I said, this isn't a good way to do it. Our field is new, right? We are working in a relatively new field that's only been around for 50 or 70 years as compared to, you know, the medical field that's been around for hundreds. So as a development, we should have modules. Let's use modular programming. This works for us because we're always breaking things apart, trying to figure out the next step. So using modules and submodules or subprograms, each module performs a single task. A module is self-contained and independent, right? If I'm going to have Joanne working on this one and Bill working on that one, they can't, you know, be crossing over into each other's territory all the time, or we're going to have some conflicts. They have to be self-contained. Each module should be short. Here they say ideally statements should not exceed 1 page. Since I've been at OTC, I have heard so many different rules about this. I've had people come in this room and say, I heard it was 5. If you have 5 statements in a module, that's too many. I've heard it was 7. Well, it's not a number of statements. It's a task. It's the number of statements that are required to perform that task, right? So my problem comes in if I start getting my module performing all sorts of different tasks. The ideal, perfect world is only 1 task per module. Now the benefits are, our program is easier to read. Each module is simple. We can look at it and understand what's going on. Each module theoretically could be designed and tested independently, making it easier for us to test things, each unit. Different modules could be designed by different programmers. We could use a single module in more than 1 place, right? All over. And modules that perform common programming tests can be used in more than 1 program. So let's think about this, a single module that can be used in more than 1 place. What about Windows? Windows does this so good, right? So if I am in any application in Windows and I choose File, Open, I'm going to have the Windows File Open dialog box display, right? That is that single module. That module is used for any application that's running on Windows that does a file open. So we always know what it's going to look like. We know how to interact with it, and we know how to use it. And the people at Microsoft, you know how to control it because.
Is that kind of like the libraries and the Arduino programming?
So your libraries are just like that. Just modules that are available to you to use for your code. Okay, so here's our pseudocode. It's a little bit longer now. So we've split things into modules. And we've said for our sales data program that we're going to have an input module that requests input. We're going to have a calculations module that does all of our processing calculations. And then we're going to have an output module. So our input is going to prompt for things and then input them. Our calculations module is going to set all our different variables to the math formula that was specified. And then our output is just going to write out our data. Now, if we just output all of these numbers like this, it's going to be kind of hard to read. So we probably want to add additional information to our output. So we want to annotate that, spice it up a little bit, put some labels on, so now we can tell what our output is. So we now have these great modules in our pseudocode. We've split things up a little bit, but we need something that controls the whole thing, right? A controller type module, a subprogram that acts like the person in charge. This controlling module then would be in charge of saying, I want to run the input module. I want to run the calculations module, so that we could get all of those different subprograms executed. So we set that up as a calling module. And in our module, we put the code for the word call and then our submodule name. The implication is that when we call our submodule, program execution will transfer from the module we're in to the module we call. Execution will begin at its first line of code or pseudocode, and it will go through all of the lines of code in the submodule. When it gets to the last statement, execution will return back to the caller. So again, just like the file dialog open, you pick the file you want and click OK, and it goes back to the original program right where you were. So that's a call. So the main program, our controller program, is always called main. So that module that runs all of the other modules is our main module. So the main module is where program execution starts and ends. It's not a submodule of another module. It's on its own. It's the parent. It's at the highest level. So our input data module, our perform calculations module, and our output results module are all going to be called by our main module.
Kind of redundant.
Do what?
So isn't it kind of redundant?
The main module?
Or maybe arbitrary. So multiple main modules, or?
No, you usually just have one main module in a program.
If you're going to have multiple, you need one above them that calls those.
Mm-hmm.
It becomes a new master.
And we'll look at a picture here in a minute. This slide seems to be in the wrong place, but it talks about how we needed to format that output of our pseudocode. And I think you guys got that. So here's our hierarchy chart. This is where we needed to go. Our main module sits up at the top. A hierarchy chart is simply a diagram that shows what module calls what modules. So in this example, we have a main module that calls module A, module B, and module C. Module B calls additional modules, B1 and B2. So I can look at this simple diagram and just see what subprograms we have in this main program. So a hierarchy chart is like a subprogram map. And it's really simple. It is just that simple, that we just want the rectangles. Now, as we're coding, we're going to be using our programming language, and we're going to be putting some comments in. We're going to have those internal comments in our code, and then we're also going to have maybe a user's guide or some other external documentation for our users. We like header comments. Those go at the top. That's what we've been putting in our pseudocode, is a header comment, right? Saying, you know, what it's about, some overview information. But then we can have step or inline comments also. And those are comments that are throughout our code. Maybe explain something that's complicated. In this example, we have a program that finds the size of a room. If you look at it at first, it's kind of hard to read to start out with all the slashes and everything. So take a look at it. Let's really read it. One of my goals here is to have you reading code. That's what we want, is look at code and just read it. First of all, I see that I've got several comments at the top. And I see that it's a program to calculate the area in square feet of a room, who wrote it, and then they have a little bit more information here. Some variables used, and then they declare their variables. Finally, some pseudocode code. I have some variables width, length, and square feet. I prompt for my length and width. I calculate the square footage and output the result. Notice too that the spaces are included in the string so that that output formatting is correct. In that chapter 1 short answers the review questions, there were some people that caught that. Be aware, if we're missing spaces, we're going to be all squished together. So we have to take care of even those little details. And then finally, we're going to test. Test data is going to be really important. We want to make sure we're using data that exercises all of our program code, not just easy data. And then desk checking again to walk through our code. Logic errors are the worst. These are errors that we encounter when the program is running, so they're called runtime errors. Logic errors are where things aren't quite right, so we have to be really aware of those. User's guide. And I wanted to show you flowcharts. When we're designing, we saw how that IPO chart, that input processing and output chart, would make things so much clearer to look at. That's because we are so visual, right? A picture's worth 1,000 words, all those kinds of stories. Well, a flowchart is like the visual alternative of our pseudocode. So it can really help us identify logic. When we're using a flowchart, we're just looking at connected symbols that are meaningful. Let's look at some of these others here. Oh, it's not going to let me get it to where I want it. I'm going to look at this first one. So in this first flowchart, it starts out really good. I like this flowchart. This symbol here, the start symbol, is actually really important, right? This is called a terminator. It's used to begin and end a flowchart. So it's really, really important, because otherwise we might not know if we're really at the beginning. Now, I'll tell you, you can see some flowcharts where you're not sure. So in this flowchart, we start here, Then we have this rectangle, which is good because the rectangle is for a process. And it says we want to check the weather channel. Over here we have an annotation, a little comment. It says the weather channel is on cable channel 61. I don't think that applies to us, but whoever. Okay, so we're going to check the weather channel. We're going to follow this line with the arrow. And then we have a decision diamond. And our decision diamond says, is rain predicted? If the answer is yes, we're going to follow this path and stay home, right? If the answer is no, if the answer is no, we're going to follow this path to go down and play golf instead. Now, no matter which way we go, whether we follow the yes path or the no path, we're going to end up down here at the stop. Right? So this is a beautiful flow chart. It uses all the right symbols. It's got arrows to tell us which way to go, and we know exactly what's going on with it. Love it. Let's see if we've got another one here. What about this one? This is a student one. You can tell when I found this one. So when I had just gotten one of those emails, okay? So it starts out without a start. So right off the bat, as a coder, I'm going to be asking questions. Am I missing part of it? Is this really the beginning? Where's the beginning? Because that's how needy I am. I need to know the start. And it starts right off with a question. Do you have homework? And if you answer no, it says, oh, you're lying. And then this arrow points into this decision diamond. If you say yes, it points into the decision diamond also. So that's kind of like an illogical situation, right, in that flow chart. It's not really doing things properly, but it is using decision diamonds. Next, is it due in less than 12 hours? Yes, better start working. So here we use the wrong symbol, and instead of showing a process, we're kind of showing the end, but that's all right. Now, if the answer is no, it's not due in less than 12 hours, we're gonna watch TV, play some games, check Facebook or something, and then go back and check the time again to see if it's due. This is really my loop, not yours, right? Now, I wanted to show you this one through a lot of reasons. First, a little bit of usage of the wrong symbols can be a little confusing, but mostly because it's got this looping. See how it's looping? So after we check Facebook, we're going to follow this path and come right back up here and check this decision again. Is homework due in less than 12 hours? Nope, still not. I can watch more TV, play some games, check Facebook again. And so I can keep looping through this looping structure until I finally hit a yes condition and go do my homework. Okay, so our flow chart can show relationships like that where we have to loop and do some things. Well, let me show you another one here. I'm trying to make it a little bit bigger because it's kind of hard to see. And then, did you really even study flowchart? Is rest your major? Lol, no. Did you go to office hours? Yeah, sort of. I skimmed. Yeah, I had questions. So we see that this flowchart is not a flowchart at all, right? It's just a crazy big old mess of stuff. So it really doesn't tell us anything at all. And unfortunately, sometimes from design meetings, we can actually end up with stuff like that. We try to avoid that. We want things to really be meaningful and to tell us what's going on so that we know we're following the instructions properly. Here's my favorite one. This isn't a flow chart. If I could get it to move. You've probably seen these before. But I always like to show these because it reminds people why it's so important to have standards, right? So this is cabling from a different country that doesn't have the kind of cabling standards that we have, or at least at this time did not have those kind of cabling standards. So you can see how the electrical wires, let's see if I can zoom in, have become all mixed up with the cable wires and the phone wires, and it's very, very dangerous, right? We wouldn't want to work on that in any sort of way. So these pictures show us why standards matter. Standards are important. Standards do matter. They are good. I know we don't all like regulations and things, but this is important, right? We want stuff that doesn't look like that. All right, so let's make our own flow charts. I'm going to show you how to create a really quick one. Before though, let's look at some of these basic symbols. We have the terminator symbol, the process, input, output, decision, the connector. Usually we can get away without using that, but sometimes we can make things neater if we have like a point A connecting to point A, so that we can have that flow chart work that way. And then our final pseudocode for our sale price program. So next time when we come in, what we'll do is we'll look at creating these flow charts and look at using Raptor to create flow charts that will respond to us so we can actually see some feedback. So we can do that. So we'll do that next time. So today, for your lab time, we have, I've closed everything out. There it is. You're welcome to stay and work on your scratch game or your chapter 3 review questions. Also welcome to get out of here. Next time, we'll look at those scratch games, look at creating some flow charts, and then we'll have some additional lab time working on this supermarket thing. So your lab time might be a little bit tied up on Thursday. Any questions before we break for lunch?
What was the word you used for the start of the program in the flow chart?
Terminator.
Terminator.
Got it? Everybody good? Okay, lab time. Make those scratch games awesome. Let me know if you're stuck and I can try to help.